Hey gang, I hope you enjoyed that fifth gear loop-to-loop video. I thought it was pretty fun. Um, so it lends itself to a quick analysis that's kind of a classic one in physics with vertical loops. And it's a situation in which you use both centripetal forces and energy to come up with a solution. So I think it's kind of important that you see it. Plus, it's kind of a fun analysis. It lends itself, it actually shows what the video is saying, how fast the car needs to be going to enter the loop, and it comes out pretty close. So it's pretty cool. So two ideas are needed to solve a problem. The question would be is, what's the minimum initial velocity of the car to just make it through the loop? I mean, you want to know that, right? So you can look at your speedometer to know, am I going to fall off this loop or am I going to make it through, or, what's going to happen here? So here's the scoop. So note that what we mean by just making it through the loop is going through the top of the loop, all right? You're going to feel all of a sudden like you're in free fall right at the tippy top. Not here or here, but right at the top. The minimum speed you would need to enter the loop, as you reach that height, you're still going to have a speed. You're just barely going to be on the track. So what that really means, let's take a look at, we start all good force problems, right, with the FBD. So if we're at the top of the loop going really fast, you'd have gravity and a normal force downward holding you on the vertical loop. But to just make it through, we let F sub n go to 0. That means to just, right? As that normal force is just approximating 0, you're just staying on the track. And so the only centripetal force at the very top then, if we let F sub n go to 0, would be gravity. Okay, so the only force in the centripetal direction is gravity towards the center, and that's mg. So what we could say is then mg, right, is going to end up equaling mvf squared over r. Vf is the velocity at the top of the loop. Okay. And we can see that we come up with a solution for that velocity squared at the top of the loop would equal g times r. So notice this would be true for any car or any object, right? It's not just that one car that they were using, but any vehicle would have to have that same requirement. It could be a motorcycle that you want to ride through the loop or whatever. Skateboard, if you're doing a loop-de-loop like thing around a skateboard in those tubes or whatever, any solution would be like this. Maybe like a motocross bike doing that, anything like that. In fact, you could even try to run in a loop. I've seen like a Pepsi challenge or something like that on YouTube. You can look it up where they've done that. But remember that anytime you see v squared, it looks like we could also use some energy ideas. So what we're interested in is the initial energy entering a loop. We've got a final velocity at the initial velocity coming into the loop. We have an expression here for the final velocity at the top. We know the initial height is 0, and we know we'd have a final height which would equal twice the radius of the loop. So if we assume no energy loss, right, and of course we would have a little bit of energy loss, but let's take the perfect world for now. It's a pretty fast event, and at least it gives us an approximation or an idea. So like all things being perfect, and we don't have any work term here on the left, we could assume some lost energy and still do the problem, but let's just go ahead and keep it simple for now. What we could see is we could set up our conservation of energy idea. Again, the main goal here is trying to find the initial velocity. Well, we'll let our initial height be 0. We're looking for the initial velocity. Our final height has to be twice the radius of the loop. And look at that. We've got an expression for Vf squared that we just found here from our forces, okay, and our condition of being just making it through the loop. So if we take that and follow that through, now our next term is to substitute. Notice again, mass drops out of our energy term, and we're left with just 1/2 vi squared equals g times our height. Our final height should be twice the radius of the loop, okay, plus 1/2 vf squared. Well, vf squared we found from our forces should be g times r. So we just kind of follow through and we realize, okay, I'm multiplying both sides by 2, all the terms by 2. That gives us vi squared equals 4gr plus vf squared, where vf squared is equal to, amazingly enough, g times r. Look at that. So we come down to this very simple solution that the square of the initial velocity coming into a loop like that has to equal 5 times g times r. Isn't that amazing? The mass drops out, all these terms drop out, and it's left down to gravity and the radius of the loop. I think that's pretty cool. So if we substitute in some numbers that were given in the video, I think I've got to get rid of my, video. I got to move myself over here. Hopefully that worked. If we let in English units, because the video was done in English units, g 32 feet per second instead of 9.8. And I think they said the height was pretty close to 40 feet of that circular structure, which gives us a radius of 20 feet. So if we do that, 5 times 32 times 20, we take the square root, that's 56.6 feet per second squared, or 38.6 miles per hour, which I think is pretty close to what they had come up with. But that's very reasonable for the car to get up to that speed, right, as it's going to enter that loop. So there's a little analysis. We could make some other, assumptions and tweak it from there, but that's the basic idea. So hope you enjoyed that.